All right. How do you add things? Well, here the terms are just growing up, kind of like a polynomial, right? And so the middle term is more or less within a constant of the last term. And so the sum is within a constant of the number of terms times the last term, right? That's good to know, right? It's for any sum where the terms grow kind of polynomially, right? Versus this one, the terms are growing exponentially, right? Every term is r times bigger, right? And then it's dominated by the biggest term, right? Which could be the first or the last. Yeah, people good with that? Are everybody quiet because you're following or because you're not following? You're not following? Okay, Holler, why aren't you following? What? He's not following. Yeah. So here's just, if I'm summing this number plus this number plus this number plus this number, right? Up to this number. And the middle number, right, is around the last divided by 8. Right? Then more or less the sum is the number of terms times the last term. Right? Because all of these terms are about the same within a constant. Right? This just says that this sum is going to be, how many terms do I have? I have n terms. What's the last term? N cubed. So the sum is order into the fourth. Well, this sort of proof by picture, right? It's dominated by the biggest guy, right? Those are, those are called arithmetic versus geometric sums. All right, quantifiers. So what do I really want everybody to know about quantifiers, right? It's a language where you really can write down useful things in math. And you should, when you have some math question, you should write it down with these quantifiers. And then you should be able to prove things. Now, are we going to be able to prove things in a multiple choice question? No, but there are quantifier questions, all right? And what do you need to know for sure in computer science is this sentence right here, right? You read it left to right. This says, what are we saying? We're saying something about machines. There exists a machine. What's a machine? It's basically an algorithm, right? There exists one machine that has what property? It has the property that you give me any input and my machine will give you the right answer, right? And how big can this machine be? Well, I can give you as big of a machine, as complicated as a machine as I possibly want, right? The only requirement is that it has a finite description, right? So I give you the machine. Its description is trillions long, right? It really memorizes a lot of things. Well, but then an adversary can come and give you a really, really big input, and it won't know how to solve it, right? Does that make sense? And that's different than this, right? This says every input has a machine that can solve it for that input, right? That you can have a different machine for every input. And that brings pain to my heart, right? Because your machine, you can't have a different machine for every input, right? People follow that? And it was sort of like here It looks, I mean, it's dating me. It looks, these are so old, right? There's probably, do you even know who this is? He was the sweetest man. He was, who was NDP, and he was doing well, but then he died of cancer, versus the conservatives, right? Here we're saying, this is a statement about politicians, right? We're saying there exists some politician that everybody loves. Has that ever happened? No, that hasn't happened. What is possible is that for every politician, for every voter, is a statement about voters, right? Every voter has the property that they love some politician, right? But it can be a different politician for the different voters, right? Everybody get that? Good. If you get that, you'll be fine for the test. Right? This is talking about polynomial, defining polynomial time and exponential time.